So interesting. Next topic also go relate to GNN. So it's presenting by Sage, Haider and Mehdi Rizvi from the QUT. The GNN and with the hybrid autoencoder, people probably familiar. Yeah, go ahead.
So let's focus on the objectives. Broadly, so broadly, objectives. So today I will cover two objectives here. The first thing is a data preservation because all we need is data. Data is very important for us. And whenever we apply different kind of a statistical model or any machine learning model, and when we convert data from one domain to another domain, we always lose a lot of information. So the first thing is data and the feature preservation. And the second thing is combining the power of soft computing method because finding damage or damage identification in a large structures uh, is not a job for a single machine learning model. It would be a very difficult for a single machine learning model to predict structural damage. So we have to combine the power of different soft computing models together. So today I will discuss two models basically. The first thing is a data preservation model. So actually my aim is to preserve uh, features in all the domain. Either it is in a temporal domain, a spectral domain, or a spatial domain. So I have to preserve these features in all possible domains. So here I use actually uh, two models. The first thing is a CNN model. This is a CNN model, and CNN models are good for preserving spatial information. And and the second model is here. It's basically a BILSTM model, which is a long short-term memory. It's a type of RNN model, recurrent neural networks, which is good for preserving temporal data. And for the spectral, I use here, this is MODWT layer, which is maximum overlap discrete wavelet transform. It's a type of time frequency analysis. It's a it's basically a time invariant time frequency analysis. So I have all of these layers and I combine them into a autoencoder fashion, into an autoencoder architecture. So autoencoder is actually used to compress the data, or compress the data and reduce into a lower dimension and then decompress it. The best part of autoencoder is that it actually preserves the vital informations because the input and output are same here. So the duty for uh, uh, basically an autoencoder would be to preserve all the information here. And I will use the that middle layer to extract the data because it would be the most condensed and compressed form of the data. So it would be a more sensitive form of a data here. So I will I will extract the data from that particular layer, that is max pool. And my second model, which is a and these all are the fully connected neural networks. And my second model, which is a main model, which is a classification model or anomaly detection model, would be the graph neural networks. So graph neural network is a very powerful neural network. It works on objectives or a nodes that share some kind of information. Because in a civil structures, if you're talking about the bridge, we have a lot of sensor that are distributed over the the deck of the bridge. So these sensors share some kind of information. So graph neural networks, they are good at analyzing those informations. So the best part is they capture both local and global node information through the neighborhood aggregation. So this is my architecture. This is my architecture for the GNN model here. So the first layer is the features which I obtained from the autoencoder model or feature extracting model, which I have already discussed in the previous slide. And the second layer is an embedding layer, which actually nothing but converts the features into more dynamic form or more learnerable form. The second layer is a graph structures. It's a n by n matrix actually that actually represents the relation among nodes. It's a weights actually that represents the relation among different nodes. And the third is the attention mechanism, which is a very powerful thing for GNN actually, because not all nodes information are vital for us. Because most of the sensors informations, they are redundant. And some informations are vital. Basically, for example, those nodes which are very close to the damage, their information are very important for us. So this layer actually determines which node needs attention. And then we have a ReLU and neural networks. So now we have two models here, which is basically a which is basically an autoencoder model, and the other one is a GNN model. Autoencoder is basically our feature extracting model, and the other model is used for the classification or anomaly detection. So we can train them individually, but the problem is the first model is an unsupervised, and the other model is a supervised learning. So the problem is our feature extracting model does not know about the ground reality. I mean, what is right and what is wrong. But the second model is a supervised learning. It does know what is right and what is wrong because it does have a ground reality. So we cannot train them individually, but we have to combine them. Basically, we have to combine those of these model and train them simultaneously. So that we can penalize both the model together. So for analogy, it would be something like if I don't like the taste of the pizza, then instead of only penalizing the chef, I will also penalize the person who is providing the ingredients. So I will train both of these network together by just combining their loss function. These are the loss function for the autoencoder plus the loss function for GNN models. And these alpha and beta values are the hyperparameters values, which is used to stabilize the network. So I will just collect the loss function from both of these models, combine them, and then back propagate to both of these networks. So both of these network will actually tries to reduce the combined loss functions. And uh, and basically this is how I actually combine the power of two neural networks here. Training and evaluation. So here I use Z24 bridge model. This is Z24 bridge model, which was in Switzerland, now demolished. Basically, there are two testing methods they used. The first thing is a FET. FET is a force vibration test. They use some kind of a shaker to shake the bridge. And the other is AVT, which is ambient vibration test with 17 different scenarios. These are the 17 different scenarios. Undamaged, lowering of pier, spalling of concrete, failure of anchor, and rupture of tendons. And these are the labels which I use for my model for the classification. Reference, pier failure, concrete damage, structural failure, and tendon rupture. On the deck of the bridge, there are 15 sensors which are distributed over the entire structures in 9 steps or in 9 setups with basically with three reference sensors here. So these are my results actually. So the first diagram represents the training losses. The first one is an autoencoded losses. The second one is a GNN, and the third one is a total losses. Uh, uh, the second diagram represents the confusion matrix, and I achieved the overall efficiency of around 94.6%, and F1 score is 86%. And the best part is I have low false negative values here. And these are the results for the force vibration test. Again, I achieved the overall efficiency of 95.6%, and F1 score is 89.4%. And when I compare it with the latest studies, relatively, I achieved a very high frequency here, 94.6 and 95.6% overall. And if I use this exact same model for the damage detection, and if I calculate the anomalous behavior of different sensor and all the 15 sensors and then combine them, I will get this beautiful picture actually. So this is the example of pair failure at pair 2. So this figure shows actually my model actually localized the exact position of the damage as well. So actually it represents how powerful GNN is actually. And the conclusion actually, I design a model to retain the sensitive spatial, temporal, and spectral features. And then I convert it into dynamic high-level graph structures by end-to-end learning and achieve high frequencies. After that, I will apply the exact same model for the different data sets through domain transfer learning, and will develop a model for the advanced detection processes as well. Thank you.
Thank you, Syed, for keeping time well. So we have time for 1 or 2 questions. Sure. Very interesting one.
Talking too much today. You had an example and efficiency of 94 some percentage. Yes.
Yeah.
How much bridge dependent is that percentage? For example, have you looked at different, less complicated, more complicated, and see whether you can improve on that? Not that it's a bad percentage, but how dependent is it on the complexity of the bridge itself?
So I tested on Z24 data, which is a pretty complex bridge. I mean, it's around 70-meter wide bridge. So yeah, it would be different for different bridges as well. I mean,
You don't have a range, for example, that it is between. I think I must suggest that you do it for a few more.
Yeah.
So that you have
That
a
would be
bit
nice.
of a comparison. That will be useful for your work.
Yes.
All right. If no more question, we can move on to next presentation. Thank you. Okay, let's put hand together again. Thanks, Syed.